Hello guys, welcome back to the channel. Hope you are doing great. In today's video, we'll start a chapter called Electrostatics. We'll start to build the ideas of charge and Coulomb's law from first principles and see how it appears in problems here. So let's start. First of all, what is electrostatics? See, this term electrostatics comes from two words, electro and statics. The term electro, it comes from a Greek word called electron. Now, what does electron means? In English, we say it is amber. Now, amber during ancient in ancient Greece, when they rubbed amber with wool, they saw this amber acquire some unique properties through which it attracts dust or small pieces of paper, the lightweight objects like feathers. It starts to attract them. So this kind of property, when later studied on, we came to know about the properties called charge. So from that umber word, from the electron, this electro word comes, and statics, it means at rest. So basically in electrostatics we read about charges at rest. You see, out of four fundamental forces of nature, electromagnetism is one of the basic fundamental force. Now in electromagnetism we read about electricity and we read about magnetism. Here, in our scope of studies, we read electricity part separately and we study magnetism part separately, even though in real nature, both coexist together. So now in this electrostatics chapter, the first basic term that we need to know is what is a charge then. See, charge is an intrinsic property of elementary particles which gives rise to electromagnetic interactions. See, the electric interactions, this comes when charge is at rest. The properties of charge being at rest we study under electricity. And what about magnetism then? In magnetism, we study about the properties of charge when it is in motion. So charge in motion gives rise to magnetism. Charge at rest gives rise to electricity. It is a scalar quantity and its SI unit is Coulomb. Now it has two CGS unit as well. The CGS units are electrostatic unit and electromagnetic unit mentioned here. The electrostatic unit we call as start coulomb and electromagnetic unit as up coulomb. Now electromagnetic unit is basically what we will read about it in magnetism. And now let's explain what this electrostatic unit is. Now electrostatic unit is, if let's say I have two charges of equal magnitude, let's say I have charge q, both are of equal magnitude and the charge amount is q, we keep them at a distance of 1 centimeter and the force of interaction between them is 1 dyne. So if two charges we keep them 1 centimeter apart and the force of interaction comes to be 1 dyne, then the amount of equal charges, these two are equal charges, right? Then the amount of charge here that should be present is called 1 start coulomb. This is how we define the electrostatic unit. Now in case of Coulomb, the way of presentation is different. It is the SI unit of electric charge. Now we know the popular charges, basic atomic structure. There electrons, protons and neutrons are present. We know about this. These electrons come under basic our subatomic particles which are called leptons. Now these leptons are little bit unique. They do not feel, this is a important property, they do not feel strong electromagnet strong nuclear force, sorry, they do not feel strong nuclear force, whereas protons and neutrons, they do feel strong nuclear force. These are actually again constituent, they have constituent particles which we call as quark particles. These quark particles have charges which is equal to plus or minus 1 by 3e or plus or minus 2 by 3e. This amount of charges are present, but again the unique nature of quark particles are they cannot be isolated. They are not isolated. They, we cannot find them alone, they will always be together. That's why also If we say we have given some material some charge, then the amount of charge the material acquires, be it positive or negative, it must be integral multiple of one electron's charge, and one electron's charge is 1.6 into 10 to the power minus 19 coulomb. So any matter which will acquire some charge, be it positive or negative, it that charge must be some integral multiple of this number, like 2 times this or 10 times this or 1000 times this, but it must be an integer number. We cannot divide it into parts. Even though in nature some fractions of electronic charge is present, but they cannot be found isolated. That's why any matter they will always get an integral multiple of electronic charge. Units of charge as well. One of the practical units of charge is 1 ampere hour, and 1 ampere hour is 3600 coulomb. Similarly, there is another unit called Faraday. See this, we should not confuse this with Farad. Farad is different. Now Faraday is the unit of charge, and its value 1 farad equals to 96500 coulomb. This is the amount of 1 farad. These are practical units of charge. So if we talk about the units as a whole, then the smallest unit of charge that we know is start coulomb, and the largest unit of charge that we know so far, that we use so far, is farad. Now out of all these units, if we try to compare them, then 1 coulomb is basically 3 into 10 to the power 9 times electrostatic unit, which is equals to 1 by 10 times electromagnetic unit. Electrostatic unit is our start coulomb and electromagnetic unit is our up coulomb. So 1 coulomb we can say as 3 into 10 to the power 9 start coulomb, which is also equal to 1 by 10 up coulomb. Let's see the basic properties of charge. First of all is additivity. The total charge on a system is equal to the sum of individual charges at different points on the system. So if we have a system in which there are many distributed charges, let's say this is plus 1 coulomb, this is plus 2 coulomb, this is minus 3 coulomb, this is plus 4 coulomb, like that, then the net charge on the system, we can add them and say this is the net charge of the system. They are directly added. Charge is a scalar quantity, so the value of net charge on the system can be directly added and we can get the net charge. Next is quantization. Charge values cannot vary continuously, it can have only discrete values, and that discrete value is a charge of 1 electron, which is 1.6 into 10 to the power minus 19 coulomb. We talked just few minutes before that charges can have 1 by 3e or 2 by 3e amount of charge, right? Plus or minus 1 by 3 and plus or minus 2 by 3. These are the quark particles. But also we discussed there that quark particles do not exist isolated. So that means this amount of charge we cannot get in isolation. In isolation, the amount of charge, minimum amount of charge that we can get is the charge on an electron. It can be plus E or minus E, doesn't matter, but the amount should be the amount of electronic charge. That's why any matter can only have total amount of charge which is integral multiple of one electronic charge, right? And also the magnitude of charge of an electron or a proton, which is same, one is just positive, other is negative. This is a natural unit of charge. Okay. Next, conservation of charge. What does this mean? Now, the algebraic sum of electric charges in an isolated system is always constant. So net charge of a system will always be constant. If it is an isolated system, the net charge will always be constant. Now, to understand the basics of electrostatics, we must first understand the fundamental interaction between the charges. That interaction is described by Coulomb's law. Now, what does Coulomb's law say? The magnitude of force of attraction or repulsion between 2 point charges. This is important, between 2 point charges. Say those two charges are Q1 and Q2 placed in vacuum at a separation r. That force is directly proportional to the product of the magnitude of the two charges, and it is inversely proportional to the square of the distance between the charges. What does it mean? Now, if we have say two charges, one here which is q1, one here which is q2, and the separation between the two charges is, let's say, r. So in that case, the Coulomb's law says the force is proportional to the product. It is proportional to, sorry, my mistake. The force is proportional to the product q1 and q2, and it is also proportional to 1 by r square, means inversely proportional to the square of the distance between them. Hence, we can say this Coulomb's force F is proportional to q1 q2 by r square, or we can say F is equals to k q1 q2 by r square, where this k is a proportionality constant. Now, what does this proportionality constant value to? We say k value is given by 1 by 4 pi epsilon naught, where this epsilon naught term again is called permittivity of free space. This is permittivity of free space. The k value amounts to 9 into 10 to the power 9 Newton meter square per Coulomb square. The k value comes to be this much, and this permittivity term, this value is equals to 8.85 into 10 to the power minus 12 Coulomb square per Newton per meter square. Now, what does this permittivity mean? Now, permittivity of free space is basically a term which gives the electric property of a medium. Permittivity of free space has this much value, but if we have electrostatic interaction between two charges in a different medium, let's say we discuss about the same thing in a different medium, this force can be written as F equals 1 by the k term I am replacing as 1 by 4 pi, instead of epsilon naught we have epsilon value into q1 q2 by r square. Here this epsilon term is can be written as epsilon naught into epsilon r. This epsilon naught term is permittivity of free space, whereas this epsilon r term is called relative permittivity. This has a name called relative permittivity. To explain relative permittivity simply, we say, let's suppose we have two charges q1 and q2, and there is a certain separation, we don't know the values, but the force of interaction between them, let's say be it attraction or repulsion, if the force of interaction, let's say it is 10 Newton. Now the entire system, if I put it in a different medium, let's say exact as it is, we keep the magnitude of the charges same, we keep the distance same, but instead of keeping it in vacuum, let's say we put it in a medium X, and the force 10 Newton, now it decreases and it becomes, let's say, 5 Newton. So the force becomes half, right? So we say epsilon r of this medium becomes 2. So if epsilon r of the medium is 2, the force will become half. Let's say epsilon r term for a medium is 5. That means force will become 1/5 of the force that those two charges experience in vacuum. Now this value of this relative permittivity, it is different for different medium. For vacuum, we consider permittivity to be 1, and to be specific, for water, permittivity epsilon r for water, it is 81. This epsilon r term is also called dielectric constant. This is just a name, dielectric constant. It is another name for the same term, epsilon r. Now, if we want to write the dimensions of epsilon, then it is m minus 1 L minus 3 T4 A2, be it epsilon or epsilon naught. But epsilon r is dimensionless. Epsilon r is basically the ratio of two terms, epsilon to epsilon naught. That's why this is dimensionless. Epsilon r term is does not have any dimension, it is dimensionless. This we need to pay attention to. Epsilon r is dimensionless, but epsilon or epsilon naught, these terms have dimensions this much: m minus 1 l minus 3 t4 a2. So dimensions of epsilon I am writing here. This is m minus 1 l minus 3 t4 and a2. Discuss about Coulomb law little bit more in detail. Now we know, we have already written F equals to 1 by 4 pi epsilon naught into q1 q2 by r square. Now if I want to write it in vector format, see here I have written F in vector format, right? So if I want to write it in vector format, then I can just write r cap here. So because let's say this is charge q1 and this is charge q2, and I want net force on q2, this is my test charge. So I want net force on q2 due to q1. Remember the term here, net force on q2 due to q1. So q1 is my source charge, which due to this one we are calculating the force. q1 is the source charge, q2 is the test charge. On q2 I'm finding the force, and the source is q1 here. So in that case, if both are same sign, let's say both are positive, in that case the force will be directed away like this. The q1 charge, if both have same nature, both are positive charge or both are negative charge, then q1 will try to repel q2, right? It will try to push it away. And if they are of opposite nature, then q1 will try to pull it. So the force will be in attractive nature. So see here, the force is along the line joining. The force on q2 if I want to write, then I want to write this r cap, where r cap is the direction vector of q2 with respect to q1. It is unit vector, but which unit vector? The direction which shows of q2 with respect to q1. Similarly, if it is attractive in nature, then it will be exactly opposite. So minus of r cap I can write. In the same term, I can write minus of I cap. So if I want to write in vector format, I can also write it this way. It is F equal to 1 by 4 pi epsilon naught into q1 into q2 by r square. But instead of r cap, I can write r vector by r again, because a unit vector is the total vector by its magnitude. So this will come down to F equals to 1 by 4 pi epsilon naught into q1 q2 by r cube into r vector. So this is our vector form, Coulomb's law in vector form. Let's color it so that we can notify it in a much simpler way. This is the Coulomb's law in vector format. Now see, the force doesn't matter what is the nature of charge. If this is positive, this is negative, then the force will be in attractive nature. If both are of same nature, both are positive or both are negative, then force will be in repulsive nature. But in any case, the forces are always along the line joining the two charges. This kind here, the force is always along the line joining the two charges. And what we call this kind of force is central force. This kind of force is called central force, where the force of interaction is always along the line joining the two charges. It doesn't matter what the signs are, right? So these kind of forces are central force. Also, electrostatic force is conservative in nature. This force is also conservative in nature. And what do we mean by conservative force? Now, in this kind of force, the work done on by electrostatic force in moving a point charge along any closed loop will always be zero. Let's say I take any charge q, move it along a path and bring it back to the same initial point, then net work done will be zero. Here The path difference, sorry, here the work done does not depend on the path. It depends on initial and final point, which we will talk more in detail when we will discuss about the electrostatic potential energy. For now, just remember that the force is conservative in nature. So if we take it, and no matter which path we take, if we bring it back to the same point in any path possible, then net work done will be zero, because it comes to the same point. The force is not path dependent. It is only it depends on only the source point from the starting point to the ending point. As it comes back to the same point, hence work done will always be zero. Now let's solve some problems on Coulomb's law. So this is our first question. Here they have given us a square arrangement of charges in a square frame. At four corners there are four charges q each, and all sides are given a. They are asking find net force on the circle charge. This is our circle charge and we need to find net force. Now let's replicate this diagram again. So here, if we see, due to this charge there will be repulsion. Similar charges are there, so there will be repulsion. So this charge will repel the circle charge this way. This charge will also push in this direction, and this charge here will push diagonally like this. So let's draw these forces. This is repulsion from the left side charges, from the left side charge. So this charge repulsion I have drawn. Now I will draw this charge repulsion, which is upward this way, and both of these repulsion are of same direction. And another one, this last one, will be diagonally in the middle of it, right? So this is how I am drawing. These forces now have values. This one will be k q1 q2, which is q square by a square. This one is also k q square by a square. But this diagonal one, as here this diagonal length, if we measure, this is a and this is a, so this one will be root 2 times a. So if I write the force, this diagonal force will be k q square by root 2 times a whole square. So now think diagonally, there is only one force, which is k q square by 2a square. But this one and this one, these two forces will also act, net force due to these two will also act along the diagonal, and this will be root 2 times k q square by a square. Hence F net will be k q square by a square, taking common 1 by 2 plus root 2. This is our answer. Similarly, if we go to another problem, here a similar but triangular arrangement of charge is given. Now if we need to solve this, again let's copy the diagram again. Now here they are asking net force on the 2q charge. Here is the 2q charge. So if we draw the diagrams, see, one of the forces will be, both of the forces will be repulsive force, hence their direction I am showing like this, the other one this way. And here they have not given, but I am taking the sides as an equilateral triangle, each side a again. So in this case, if each sides are a, then this angle will be 60 degree. Hence, as this is 60, this angle will also be 60 degree. So I can write the two forces, the values of the two forces, they are k q square by a square, and this one also, sorry, 2k q square by a square. This is also 2k q square by a square, because individual force is k q into 2q by distance square. So that's why it will be 2k q square by a square. The resultant will be in the middle this way, and this force will be resultant of the two. So I can write, if I take one of the force as F, so other will also be F, but their angle between them will be 60 degree. So F net, I can write F square plus F square plus 2 into F into cos 60 degree. This one's root over. This comes to be root 3 times F. So our F net we get as root 3 times 2kq square by a square, which is 2 root 3 kq square by a square. So this is the answer of this question. Coming to this question now, we have been given a arrangement of charge. So here at the origin we have a charge q, but beyond that there is a specific arrangement, and we can see all the odd charges are positive and all the even charges are negative, and the series goes on till infinity. So now to solve this, let's copy the diagram and we'll see the pattern. So here we can see, let's say the force of interaction between the first two charges, if we see, let's say the force of interaction we are seeing between these two charges, then the force we can write as k q square by l square plus, now it is about the next arrangement. Now q and 2q, because they are asking the force on the origin charge, right? So origin charge and the next charge, these two forces we can write as minus 2kq square by, distance is 2l, right? So 2l whole square, again plus. Now we'll see the arrangement between first and third. First and third says 3 times kq square by 3l whole square. Next one will be negative, but how much? 4kq square by 4l whole square. And the series continues like this. If we see it, let's say we take k q square by l square term as common. So in that case, we see a pattern 1 minus 1 by 2. See here, in the numerator we have 2, but in the denominator we have 2 square, which is 4. It cancels out and gives us 1 by 2. The next one similarly gives us plus 1 by 3. Next one minus 1 by 4, and so on. Like this, the series continues. Now, for infinite series like this, let's check one expression, mathematical expression. If we are asked ki what is ln 1 plus x, what is the series expansion of ln 1 plus x? The answer is x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, and so on till infinity. Now in this, if we put x value as 1, we get our required series here. So that's why we can say that this entire term is basically kq square by l square into this entire term we can replace as ln 1 plus, instead of x term right here we can write 1 again. So our final answer is ln 2 kq square by l square. So this is the answer. Now let's see the next problem. The question is like this. Here you can read the question, take a moment and read the question, pause the video here. Now I'm explaining. Let's say q1 charge is here and this is q2 charge. The distance between them is given as 3 meters, and they are asking, they have said here that the two forces, the two forces total combined, the two charges combined is 20 mu coulomb, and the net force that exerts between them is 0.075 newton. So if we write it mathematically, two charges separated by 3 meter distance, then the force F should be k q1 q2 by r square and F is given as 0.075. This amounts to 9 into 10 to the power 9 into Q1 Q2 by R square, but R is 3 square. From here Q1 Q2 amounts to, let's say I write it as 75 by 1000 into 9 by 9 into 10 to the power 9. So our answer comes 75 into 10 to the power minus 12. Here, this 10 to the power minus 12 term, we can see it is 10 to the power minus 6 square, and 10 to the power minus 6, it is a product of two charges, right? And each charges in microcoulomb unit. So their product will be microcoulomb square if we take the unit. So we can write it as 75 microcoulomb square. This is as the unit. So now they have given us that the combined charge is 20 Newton here. The combined charge is 20 Newton, sorry, 20 microcoulomb. So I can say Q1 plus Q2 equals to 20. Mu coulomb I am not writing for now, because both the units I have already matched. This one is mu coulomb, this is mu coulomb square as the product. So I am just calculating the values. Q1 plus Q2 is 20 and Q1 Q2 product is 75. So from these two I can say Q1 minus Q2 will be Q1 plus Q2 square minus 4 Q1 Q2. This one's root over. I am just using a minus b square equal to a plus b square minus 4ab, that expression. So here Q1 plus Q2 is 20. So this is 20 square minus 4 times 75. This one's root over, which gives us 10. Now we got Q1 plus Q2 as 20, Q1 minus Q2 as 10. Solving this, we can get Q1 equals to 15 microcoulomb and Q2 equals to 5 microcoulomb. And this is the answer. The two charges are 15 and 5 microcoulomb. Now let's see this question now. Here it says a charged particle whose mass is m and charge is q1 is revolving around a fixed charge which is minus q2 in a circular path of radius r, and they are asking us the period of revolution. So for now, let's draw the circular path. Here, let's say this is the charge. I'm zooming in. Now, this one's velocity, let's say it is v naught, and the radius of the circular path they are given us as r. So see, if it is the mass is revolving in a circular path, then the necessary centripetal force here will be given by the gravitational force, because it is revolving in a circular path, right? So in that case, it needs a force which acts towards center to act as centripetal force. Here that force will be the electrostatic force. Sorry, it is electrostatic force. So K Q1 Q2, here Q is small q, wait. So K Q1 Q2 by R square acts as centripetal force. So I can say it is mv square by R. So from here R gets cancelled out. I get V naught to be K Q1 Q2 by mR. So this is V naught. Now for time period of revolution, the total distance need to be covered is 2 pi r. So for t I am writing this is 2 pi r by V naught. That is 2 pi r by V naught is K Q1 Q2 by mR. So my answer comes to be 2 pi mR square by K Q1 Q2. K value is 1 by 4 pi epsilon naught here. So this comes to be our answer.